Welcome back to my YouTube channel. In the course of this video lesson, I'll be solving different practice questions that cut across different topics in the subject chemistry. Now let's get into the first practice question, and the question says, which of the following terms indicates the number of bonds that can be formed by an atom? They gave us different options. Option A here is oxidation number. Option B is valence electron. Option C is atomic number. And option D here is none of the above. That's none. So how do we solve this question? It is extremely very easy. We have to understand what this question is asking us to do. Because from the look of things, they said, which of the following terms indicates the number of bonds that can be formed by an atom? So this atom here they are talking about can also be replaced by an element. You know, in chemistry we have different elements. In chemistry, currently, we have about 118 elements to be discovered. So they're not asking us, when a particular element is standing alone, what actually determines the number of bonds that element should have? Are you following me? It is extremely very easy. Now, let us analyze this question together. I already said that this word atom can also be replaced by the word element. And I want to pick out an element in chemistry. And that element I'll be picking out is carbon. Now, they're not asking us what term describes the number of bonds that carbon should have. You know, I can actually look at how the bonds is. You know, bonds can be like this. Are you following me? But this is not the exact number of bonds that carbon should possess. Are you following me? So then I ask not what is used to determine the actual number of bonds that carbon as an element should have. That's what the question is talking about. So option A here says oxidation number. Is oxidation number the answer to this question? No, it is not. Because oxidation number, they are simply electrical charges that are found in elements. Now, this is what I mean. Just watch closely. Let's take an example. A compound, NaCl. Look at what I said. I said that oxidation number, they are electrical charges that are found in elements to form a compound. Are you following me? So this is a compound. So you know that this compound has how many elements? Two elements, which are, we have sodium, Na, and also we have chlorine here, Cl. Actually, both of them combined together. That's why this was formed. And actually, the way they actually combine is this. For me seeing this, I already know the charges that they possess. And we have to know that sodium is a metal, and metals generally they have positive charge. Chlorine is a non-metal, and non-metals generally they have negative charge. So on this, me seeing them existing like this, just NaCl, I will know that because I already know how compounds are formed. So then I will know that sodium was like this initially. Sodium is just Na+1. Listen carefully. Whereby chlorine it is, you know, chlorine oxide is minus, so it's actually Cl-1 as well. Whereby when both of them combine, in the sense that, you know, if you want to form a compound, the charges should combine to each other. The one here will come here. So the one for chlorine came over to sodium. Are you following me? So that's why we're having Na1, and this one for sodium came over to chlorine. That's why we have here Cl1 as well. And you know that when we're having one written in front of a particular element, we know that that is negligible. We can actually just remove that one. Are you following me? So this is best to be written as just NaCl. So the point here is this. All of this said now, what's the oxidation number of chlorine? -1. What's the oxidation number of sodium? +1. Are you following me? So in summary, is it oxidation number that describes the bond that an element should have? No. You can say that oxidation number is even related to how compounds are formed. It does not have any business with the number of bonds that is seen in an element. We already explained that this is carbon, and carbon can have a bond. This is the bonds. So, but this is not the exact number of bonds that should be in carbon. I'm using carbon as an example. I can use any element at all, but just watch closely. You can see that oxidation number can never be the answer. Because for instance, if you're having something like CaCl2, I believe you can actually deduce the oxidation numbers for the two elements. This is calcium, this is chlorine. Now listen carefully. You know that there is exchange of charges for we to form all of these compounds, and you know that this 2 is here. This 2, where do you think is coming from? It is coming from calcium. I'm just trying to explain the overview. So this is actually initially Ca+2, and this is chlorine Cl-1. Calcium is also a metal. It is positively charged. So the point I'm trying to make here is this. So if you observe how this guy was formed, you can see that the 1 here came here and the 2 here came here. Are you following me? So the 1 is here, invisible 1 here, which I can actually just remove because it's negligible, and the 2 is here already. The 2 is here, which is written here. Are you following me? So is it oxidation number that talks about number of bonds? No, it is not. So oxidation number can never be the answer to this question. So let's work towards option B. For option B, you saw the road valence electron. So what do we understand by the word valence electron? I'm about explaining that now. It is actually very easy. What do we understand by the word valence electron? So this is very, very easy. So we have to understand that valence electron is simply the outermost electron that is found in an element. Watch closely. I want to use carbon as an example. I can use any element, but I want to use just carbon. I can decide to use any element at all, but I'll be using just carbon to explain this so that we can actually understand the overview. So I said that valence electron is simply the outermost electron that is found in a particular element. When we draw the the diagrammatic notation of that element. Now this is what I mean. So remember, if you look at carbon in the periodic table, or if you look at carbon when you count the first 20 elements, what number is carbon? Let's go. Hydrogen, helium, lithium, beryllium, boron, carbon. This is number 6. So carbon is number 6. Wow, carbon is what? Number 6. It is very, very important you should know this. Carbon is what? Number 6. So put that in our mind. So let us draw the diagrammatic notation of carbon. This is what I mean. Diagrammatic means that those circular diagram for to which elements are drawn, whereby this is the first, this is an atomic structure now, whereby at the center we have something called the nucleus. I believe you know this diagram. It is very, very important. This is the nucleus, this is an atom, okay, and the atom we are working through now is carbon, whereby this is the first shell drawn. We have different shells. For atom, we have the K, we have the L, we have the M, we have the N, we have the O shell. KLMNO shell. Do you understand? So this is the first shell, whereby for the first shell, the maximum number of electrons that should occupy the first shell is 2 electrons. Since carbon is number 6 and it is neutral carbon without a charge, did you say I wrote plus or minus? No, I did not do that. So it means that since it is neutral carbon and carbon is number 6, it tells us that the electron number of carbon should be 6 as well. I already have all of this in my video lessons on how to determine the numbers of protons, electrons, and neutrons in an atom. Okay, it's good you go watch those introductory videos. But in this video lesson, I'm still going to make sure that you understand the rudiments to how questions under this aspect are being tackled. So this is the first shell drawn, and I said that this first shell occupies a maximum number of how many electrons? 2 electrons, which I have drawn here already. Whereby any other cycle I'm to draw should occupy 8 maximum. Do you understand? So here now this 2, I want to draw another, which is this. Okay, let's just remove atom. So I said that the next cycle or any cycle to be drawn after this should occupy 8 maximum. So you see, if you observe, what's the total number of carbon? 6. Carbon is like, number 6 in the periodic table. So we've written for just 2. So how many is remaining out of 6? 4. So let's draw for the 4. 1, let's just say 2, 3, and 4. You can see I've drawn 4 outside. All these things, they denote electrons. 4, 2, what's that? 6. So now they are asking, is it valence electron that determines the number of bonds an element should have? Yes, it is actually valence electron. The answer is option B, but I will explain. It's not just me saying that it's valence electron. I have to tell you why it's valence electron. So you can see that at the valence shell, this valence electron means electrons in the outermost shell. This is the outermost shell. And how many electrons are here? 4 electrons. So since you're having 4 electrons in the outermost shell, it tells us that.
Alright guys, a quick one. Now this must be noted. Now, we've all agreed now that it is the valence electron that is seen in a particular element is what determines the number of bonds that that particular element should have. You can see that for this question number 1, the answer to the question is valence electron, because it is what determines the number of bonds a particular element should have. That is why the answer here is option B. But let me explain. Listen carefully. Now, in this aspect, we have to note 2 types of configuration a particular element should be in. We have 2 of them. The first of them is called the octet configuration, and the other is called the duplet configuration. Now, from the word octet, now, what I'm trying to say here is this. When elements are to bond together, are you following me? When elements are to bond together, we must make sure that they are bonding to become stable. Are you getting what I'm saying? When element bonds together, the reason why they are actually forming bond is to make sure that they become stable. Do you understand? So when I talk about octet configuration, I mean that that element should have a maximum number of 8 electrons. Octet, 8 electrons. But when I talk about duplet configuration, it means that that particular element should have a maximum number of 2 electrons. Are you getting what I'm saying now? So on this, if you check, at the end of drawing the diagrammatic representation of carbon here, I can actually use any element. Do you understand? I'm just using carbon as an example. At the end of listening to all of these teachings, it is best you practice. Do you understand? So on this, if you check, at the end of drawing the diagrammatic representation of carbon, how many valence electrons was seen at the outermost shell of carbon? We saw how many valence electrons? 4. So what did I say? For a particular element to be stable, it must be in like 2 configurations. It can be in either the configuration of 8, which is the octet configuration, or the configuration of 2, which is the duplet configuration. Are you guessing me now? So now you can see that we had 4 electrons in the outermost shell of carbon. So how many electrons do you think I should add to that 4 electron? Because I said that, listen, because I said that the first shell is the K shell, and it occupies a maximum number of 2 electrons, whereby any other shell to be drawn, any other cycle to be drawn should occupy a maximum number of 8 electrons. So now we've seen that carbon had how many electrons? And the outermost shell, 4 electrons. So then, how many electrons do you think we can add to that shell to make sure that that shell number of electron is complete, and to make sure that carbon is stable? Because I said that the highest is the octet configuration. So then I will add 4 electrons to that outermost shell. So you can see that that electrons I had is what specifically determines the number of bonds that particular element should have. So you can see I've added 4 electrons to the valence shell, making it all together 8 electrons. So in summary, you can see that it is the number of electrons added to the outermost shell of carbon. Because I'm using carbon as a case study now, because the number of electrons I added to, the outermost shell of carbon was 4. That was why the number of bond that should surround carbon as an element, that is why the maximum number of bond carbon should possess is 4. Because 4 electrons is needed for carbon to be stable. What does that mean? For carbon to attain the octet configuration. Do you understand? It can also work for duplet configuration in other elements. Do you get? So what you have to do for me is, look at other elements and practice before you get to understand this particular aspect so well. But most importantly, know that it is the valence electron that determines the number of bonds a particular element should have. I'm just, trying to explain further so that you can understand better.
The numbers of bonds that should on each, it should be 4 bonds. Are you following me? So look at the bonds. 1, 2, 3, and 4. It's the valence electron that determines the number of bonds and elements you have. So the answer to this question is option B. It is not atomic number, because atomic number is just the number to which the element is arranged in the periodic table. Like hydrogen is not the first element, like 1. Hydrogen atomic number is 1. Helium 2. Lithium is number 3. All of these are atomic numbers. Do you understand? Hydrogen, helium, lithium, beryllium, boron, carbon. When you count down to the first element, you know, when you count it, that those guys you count, they are your atomic number. So that can often determine the number of bonds that should be in a particular element. I believe you understand how this question was solved. It is very, very easy. Now, if you find my video lessons helpful, make sure you click on the subscribe button to my channel and also share these lessons with your friends, so we get over to the next practice question. Moving further, let's get into the next practice question, and it says a blue solid T, okay, a blue solid T which weighed 5 grams. So the initial mass of that solid, take note of this state of matter, it's very, very important. It will help us on this question. Which weighed 5 grams was placed on a table. After 8 hours, the resulting solid, so after 8 hours, what was formed? What was formed was still a solid. Please watch, it's very, very easy. The resulting solid, that's what was formed after 8 hours when we actually placed this blue solid on a table which weighed 5 grams initially. So after 8 hours, the resulting solid, it was still a solid, was found to weigh. So after we place the solid in that table, after 8 hours, the weight of that solid, you know, increased a little. Initially it was 5 grams, which is 5.0, which is same as 5, and after 8 hours it's changed to 5.5 grams. Wow. So was there an increase in the mass or decrease? Increase, because you can see that when I add plus 0.5 to this, it will give me 5.5. Are you following me? Mathematics. 0.5 plus 5.0, that is 5.5. Wow. So it tells us that after 8 hours the mass was increased. Okay, it can be inferred that substance T is what? So it can be said now that what is this substance T? Because we kept substance T in a table, but after some period of time, the mass of substance T changed and it increased. What happened to substance T? That's what they're asking us to. That's what they're asking us to actually denote. And what is that substance T? You can see what they wrote here in the options. So let me quickly explain something. When a compound on exposure to the atmosphere, it actually, you know, absorbed water. Because this substance now, it has the ability to absorb something. And what's absorbing when it's exposed to the atmosphere is water. It absorbs water to increase in weight. But listen, it absorbs water to become sticky, but not form a solution. When that substance absorbs water to become sticky and not form a solution, we simply say that that substance is hygroscopic. Listen carefully, it absorbs water to become sticky, not forming a solution. It is hygroscopic. But when you absorb water to form a solution, then you are deliquescent. Now, if you observe, how can I know that this substance is either deliquescent, hygroscopic, option C or option D? How do I know the correct answer to this question? It's very easy. They told me initially that that substance was a solid initially. But at the end of absorbing water to form 5.5 grams, it was still a solid. So do you think that that substance changed to become a solution? Because sometimes when you're in solution, you basically exist most times in liquid form. So the state of matter is supposed to change. So if the state of matter change, then I will say that that substance is deliquescent. Because for a substance to be deliquescent, I explained that it will absorb water to form a solution. This one forms a solution. A solution is formed. But for this one, the substance just becomes sticky. Are you following me? Though both of them absorb water. This one absorb it to become sticky, absorb water to form a solution. Option C can never be the answer. Has some molecules of water. Did they even tell us that? No. Get that out of your mind. Option D, it's efflorescent. Efflorescent, like the opposite of this. Efflorescent has a lot of water. So when you expose it to the atmosphere, it loses that water. Is it what the question is talking about? No. If this mass decreased, then my mind should be going over to efflorescence. Do you understand? That substance will not be called an efflorescent compound, which you are seeing here. But the mass did not decrease, it rather increased, so it's going to be between two of them. But we've now denoted that it is option B because the substance state of matter still remained as solid. So it did not form a solution, but rather it becomes sticky. Okay guys, moving further, let's get into the next practice question. And the question says, that's question number 3, it says the oxidation number of manganese in this compound KNNO4 is. So here is the compound. They are asking us to determine the oxidation number of manganese. So looking at this compound, where is manganese? Manganese is symbolized as Mn. So we are looking for the oxidation number of Mn, which is manganese. And to do that is extremely very easy. Here is the compound KNNO4. So for we to get oxidation number, we have to know some, some rules. It must be noted here that the algebraic sum of all the oxidation number found in a compound should be equal to 0. So when we see something like that, what I just said, let me just summarize it. When we see something like this, first of all, they ask us to get oxidation number, we simply equate everything to be 0. That's what we should know. Do you understand? That's what we should note. So on this, we have to now know some basic rudiments, which are, like, I can see the first element, which is symbolized as K. I know that that particular element is potassium, and I have to know that potassium oxidation number is what? It's simple to get. Potassium is a group 1 element, and group 1 element, they have the oxidation number to be +1. Are you following me? But it's something you should know. Potassium oxidation number is what? +1. So underneath potassium, I'll write +1. We are looking for the oxidation of manganese. So as I'm done with potassium, the next sign to write is plus, not minus, not divide, not times. So +1, we are done with potassium plus manganese. What's the oxidation number? That's what we are asked to get. So here become Mn still. I'm done with manganese plus oxygen oxidation number. Like in most compounds, oxygen oxidation number is -2 in most compounds, but in few other compounds like peroxide, superoxides, the oxidation number varies. But in most compounds like this, the oxidation number of oxygen is -2. You can see that I've written plus. We are on oxygen, so it's going to be -2. But I don't want to interfere with this plus for now, so it's going to be -2. And how many oxygen do we have? We have 4 of it. So it's going to be -2 times 4, close bracket, equal to what? 0. Are you following? It's very, very easy. So the next thing we do is to evaluate our bracket. So -2 times 4, that is -8. 2 times 4, 8. So -2 times 4, -8. So we are having here to be +1 plus Mn plus bracket -8. Here is -8 is equal to 0. Listen carefully. I believe that you already know that when plus and minus, interfere. Plus times minus, what are we having? Minus. So I'm going to write them here. It's going to be +1 plus Mn. So plus times minus, minus. Plus times minus, minus. Minus times minus plus. Hope you know this simple mathematics. So it's going to be -8 is equal to 0. So Mn, making it subject, is going to be 0 is already here. -8 coming here. What are we having? +8. Because it has crossed the equality sign. -8 crosses +8. Here was +1 crossing the equality sign. It should change to -1. Are you following me? So Mn will now be equal to 0 plus 8 minus 1. So +8 minus 1, that's +7. You have to be careful because they might actually write -7 in this option. So you have to know which one is +7 and which one is -7. So the answer to this question becomes option D, +7. It is extremely very easy. Are you following me now? So before we progress to the next practice question, which is on organic chemistry, I have to give you one practice question so you can master this particular practice question. And the one I'll be giving you to solve is to calculate for the oxidation number of, all right, I've gotten it, H2SO4. You should calculate for sulfur for me, whereby hint, oxidation number of hydrogen in most states is +1, 2. Do you understand? So I believe you can do that. Oxygen, you already know it, the one I used here. Are you following me? So let's get into the next practice question, which is on organic chemistry, specifically naming organic compound. Okay guys, moving further, let us name this compound together. It is extremely very easy. And now, first of all, looking at this compound, you know, I already have a full video lesson where I explained the rudimentary aspects to how you can name organic compounds from the scratch. Do you understand? So it is important for you to go watch that lesson. That video lesson have impacted so many lives. So you should be one of them, okay? So let us solve this question together. In solving this question, I'm still going to take it from the scratch as done in that video lesson. So when we see compounds like this, what do we do first? We have to actually just look at the compound and try to denote what type of compound is this. Now, in the look of things, I can see that it has single bonds. Because if it has another special bond, it will be noted. It was not noted. I'm seeing single bonds. So I know that, oh, this compound should be something. This compound should be an alkane. Because alkanes, they have single bonds all through. So the name of this compound should end with ane. Are you following me? A-N-E. So another thing we must know. The first step, let's go. Identify the longest continuous carbon chain. How do I identify the longest continuous carbon chain? You have to look at the compound, the carbon-carbon connection, and try to determine the one that is longest. Just watch. Let's do it together. I think I have seen the longest continuous carbon chain. You know, carbon can actually stand alone, whereby I will spread these 3 hydrogen. You know, I explained that initially, whereby I can actually put bond here to make sure that 3 hydrogens are here. But let's just condense everything. Now, it is in the condensed form. I already have a video lesson on how to write this type of compounds, like how to write the condensed formula of a compound, how to write the structural formula of a compound. Are you following me? I already have organic video lessons that will help you do that. So on this, I have determined the longest continuous carbon chain. This is the longest continuous carbon chain. So after determining the longest continuous carbon chain, you have to number the longest continuous carbon chain both forward and backward. So here is it. 1, 2, 3. We have numbered the carbon. Here is 4 and here is 5. Backward. 1, 2, 3, 4 and here is 5. I've done something. After I identify the longest continuous carbon chain, you number it and you name it. So listen carefully. At the end of numbering both forward and backward, you can see that we had how many carbons in this compound? How many carbons, like in the longest continuous carbon chain? How many carbons in the longest continuous carbon chain? Forget about this. This is now a branch because it was not denoted as the longest continuous carbon chain. So you can see that at the end of numbering, the highest number I had was 5. That means we have 5 carbons. So whenever we have an organic compound with 5 carbons, that compound should be pent. Do you understand? Pent, and this compound is an alkane, so it should be pentane, but we are not done. When an organic compound has 1 carbon, the first name should be met. So if it's an alkane, it should be methane. If it's 2 carbon, et. If it's an alkane, it should be ethane. If it's 3 carbon, prop. If it's an alkane, it should be propane. 4 carbons, boots. If it's an alkane, it should be butane. And now 5 carbons, so that's why it's pent. And it is an alkane, that's why it's pentane. But now we have a branch. How do we now denote the number for our branch? Simple like ABCD. So we have to note something. The branch should have a low number as possible when we are counting. So if you observe, when I counted forward and also I counted backward, what was the number to ascribe to the branch? When I counted like this, I said that the branch should have a low number. Take note, should have a low number as possible. So when I counted forward, so the branch was on what carbon? Carbon 2. Here is it, carbon 2 now. It's in this branch is the carbon, this carbon 1, carbon 2. When I counted backward, what carbon was it found? Carbon 4. So can we take the backward direction? No, don't do that. You get? Don't do that. You have to count for forward, but it's not always forward. It can actually change irrespective of how the compound is drawn. That's why you should not just count that you count forward always. Check both of them. The one that is smallest, you go for it. So you can see that I had forward direction counting to be smallest for the branch, and it fell under carbon 2. So, and this branch has a name. It is called methyl. Do you understand? It has a name. It's called methyl. So definitely it should be 2-methyl pentane. And between numbers and letters, we use hyphens to separate them. Between numbers and letters, what do we use to separate them? Hyphen, like this dash. So it should be called 2-methyl-pentane. That's the name of this compound, 2-methyl-pentane. In my organic chemistry video, I start from the introduction on how to name organic compounds, okay? So go watch that video. I'm going to put the link here in the description. So moving further, question number 5 says, an efflorescent compound is a substance that what? So I've explained this initially. To have more understanding about chemistry calculations and solving all of these type of questions, I already have them on the chemistry masterpiece, okay, which is calculations and keynotes in chemistry. So if you are preparing to write the JAMB exam, this book is very, very important for you. Now, for more information getting the chemistry masterpiece, do well to direct message me via my WhatsApp number. It will be on the screen. What did I say? I said that efflorescent compound, when they are exposed to air, the water found in them, they will be, it will be given off. That's what you should know for efflorescent. That's what you should find in this option. The water they have, it should be what are giving off to the surrounding. So let's go. Absorb water from air. Do they absorb water or their water is giving up? Their water is giving up. Option A can never be the answer. Option B, give out its water of crystallization. Very correct. You don't even have to check other options. Option C is capable of giving off colored luminosity. Did we talk about anything like color? No, we did not. So that's out. Option D, none. So the answer is option B. Whereby question number 6 says, the general formula of alkyl halide is what? Alkyl halide, alkyl can be symbolized as arrow and halide is symbolized as X. And this arrow, which is alkyl, it can also be written in form of this, as this rather. Alkyl general formula is CnH2n plus 1. This is the general formula of what we call alkyl. Alkyls, they are derivative of alkane that lost one hydrogen. Alkyl, they came from this family. When I remove one hydrogen from this family, they become alkyl. So you can see that I said the arrow is symbolized as this, CnH2n plus 1. So I can just replace my X here. Are you following me? Are you following what I just said? So please check the option that has what I just wrote. Option B has it. Did I say alkyl is CnH2n plus, minus 2? Did I say that? No, I did not. Did I say alkyl is CnH2n plus 2? No, I said it is plus 1. So the answer to this question goes to option B. So moving further, question number 7 says, industrial preparation of NH3. NH3 is ammonia. Is by what process? The answer is Haber process. This is the process used to form ammonia. Okay, Haber process. Question number 8 says, the chemical formula of plasters of Paris is what? Plaster of Paris has this chemical formula to be CaSO4.H2O. So this compound, that's the chemical formula of plasters of Paris. They call them POP. POP. It is used, they are used to, as plaster cast to treat broken bones. Do you understand? POP, plasters of Paris. So moving further to question number 9, says, brass is a mixture of what? What forms brass? It's very easy. The major element that forms brass is copper. And what becomes the other element? It is zinc. Copper and zinc. Zinc is symbolized as Zn. Copper and zinc forms brass. But if they ask us for bronze, the major element is steel copper, but it is not zinc, but rather tin. And tin is Sn. Are you following me? How did I even know? It's simple. For brass, are you not seeing SS forming it at the end? Just change it to the opposite. What's it like? Like this SS, and I said it's what? Zinc. Like S now, zinc. What's it? Z, right? Here is S. So I call this zinc. Here is Z, I call it tin. Are you understand? Like, I'm changing it. S. I just interchange so it to be easy for you to remember always. I believe you understand what I just did. It's simple. But if you cannot understand the way I explained it, you can actually just know it as I've said it. Do you understand? But I just tried to tell you like a trick on how to remember them always. Last question, it says, graphite exists naturally as what we call plumbago. This must be noted. So guys, we've come to the end of this video lesson. If you find my video lesson helpful, make sure you click on the subscribe button to my channel and also share my video lessons with your friends. Thanks for watching.